After ISO, 2 other infrared space telescopes were launched. The Japanese Akari, for which ESA is supporting the data processing, and NASA's Spitzer Space Telescope. New discoveries led to an even deeper understanding and provided new questions to answer. These previous infrared satellites provided astronomers with a glimpse into the infrared universe. To learn more, astronomers need a telescope large enough and sensitive enough to gather the light that has travelled from the very faintest, most distant galaxies. ESA's Herschel Space Observatory is the largest space telescope ever, the first of a new generation of space giants.
The 3 scientific instruments on board Herschel have a far superior sensitivity and resolution than previous infrared space telescopes. The Photoconductor Array Camera and Spectrometer, or PACS, is a color camera and imaging spectrometer. PACS can study young galaxies and star-forming nebula. It is the first instrument capable of obtaining the complete image of an object at once. The Spectral and Photometric Imaging Receiver, or SPIRE, is designed to exploit wavelengths that have never been studied before. It is a color camera and spectrometer and can study the history of star formation in the universe. The heterodyne instrument for the far infrared, or HiFi, is a high-resolution spectrometer. It is also designed to observe unexploited wavelengths and is able to identify individual molecular species. These are fundamental in the study of solar system objects, star formation, and galaxy development. The instrument detectors are cooled to a temperature close to absolute zero by a cryostat of helium that sits underneath them. The instruments and the cryostat are surrounded by thermal shields. This is the payload module of Herschel and is located underneath the huge primary mirror. The service module, housing the instrument's electronics and communications hardware, sits below the payload. Herschel's primary mirror is more than 4 times larger than any previous infrared space telescope and can collect almost 20 times as much radiation. The mirror is so perfect that irregularities on its surface are less than 1,000th of a millimeter high.
Herschel will probe deeper into the infrared than ever before, and it will open a completely unexplored infrared window onto the universe. Over half the energy in the universe that has been created since the time of the cosmic microwave background has now been reprocessed into infrared. Herschel will observe the peak of the spectrum of this light, bridging the gap between wavelengths used to detect the cosmic microwave background and shorter infrared wavelengths. Observations in this region of the infrared spectrum will provide crucial information about the history of star formation in the universe. Through the spectrum, Herschel will be able to identify the peak in star formation that occurred a few billion years after the Big Bang, and may tell what sort of galaxies contributed to this peak. As well as this, Herschel will study the formation and evolution of galaxies. Currently, it's not known if all galaxies form in the same way. Closer to home, Herschel will investigate the process of star formation in detail and take a census of ongoing star formation within our galaxy. Besides this, Herschel will explore the cold, dark bodies of the outer solar system and the chemistry of atmospheres of objects such as comets and planets. The Herschel Space Observatory will open a new window onto the universe, which could lead to thrilling discoveries that cannot be predicted. The entire story of the evolution of the universe is told through the electromagnetic spectrum. Each mission that covers a different portion of the spectrum plays a unique role in telling this story, or tells a different part of the story. The pioneering Herschel Space Observatory is set to further revolutionize our understanding of the cosmos. I'm Rebecca Barnes. Thank you for watching the Science at ESA podcast.